Imagine a blistering summer day. The pavement under your feet feels like it could melt your shoes. Meanwhile, the metal beams on a nearby construction site expand and creak, straining against their joints. This thermal expansion can be a destructive force, causing bridges to buckle and roads to crack. But here's a twist. Railroads, which stretch for miles and endure extremes of weather, don't seem to need expansion joints like other structures. How is that possible? Let's embark on a journey to uncover the engineering marvels behind this question, a story that spans history, science, and ingenuity. The railroad has been a cornerstone of industrial progress since the early 19th century. These iron veins connected cities, carried goods, and revolutionized travel. However, the challenges were monumental. Engineers in the 1800s faced a persistent problem: temperature-induced rail expansion. Without proper solutions, rails would warp, twist, and derail trains, posing serious risks. Early railways used short iron rails connected by gaps. These gaps, essentially primitive expansion joints, reduced the risk of buckling. But they introduced a new issue: the infamous clickety-clack sound as trains crossed joints. This constant impact wore down wheels and tracks, demanding frequent repairs. Enter steel, a game changer. Unlike iron, steel offered superior strength and flexibility, enabling engineers to rethink rail design. Modern rails, often hundreds of feet long, eliminated the need for frequent joints, paving the way for smoother, safer travel. Thermal expansion is the tendency of materials to expand when heated and contract when cooled. For a railroad track, this phenomenon is unavoidable. Steel rails, for example, expand about 1/8 inch for every 100 feet with a 30-degree Fahrenheit temperature change. Over miles of track, this adds up to substantial movement. To manage this expansion, engineers rely on two critical innovations. Modern railroads use CWR, where long sections of steel are welded together to form a single, continuous track. This design eliminates the need for traditional expansion joints. The track is held in place by anchors and a bed of crushed stone, ballast. These components distribute forces evenly and prevent excessive rail movement. Despite these advancements, railroads aren't immune to challenges. On exceptionally hot days, rails can experience sun kinks, sudden, dangerous buckling caused by thermal expansion. Imagine the stakes: a high-speed passenger train hurtling toward a section of warped track. The potential for catastrophe underscores why meticulous maintenance and monitoring are critical. Engineers use advanced tools like thermal imaging and track sensors to detect stress points before they become hazards. Have you ever wondered how engineers predict and prevent such dangers? The answer lies in a combination of cutting-edge technology and good old-fashioned vigilance. Let's take a closer look at how continuous welded rail works its magic. Unlike older tracks, CWR relies on the inherent strength of steel and the precision of modern engineering. By pre-stressing the rails during installation, engineers ensure they remain stable across a range of temperatures. Pre-stressing involves heating the rails to a neutral temperature during installation, a carefully calculated midpoint between expected extremes. This process locks the rails in place, preventing expansion or contraction from causing significant movement. But what happens if temperatures deviate wildly from expectations? That's where ingenious design meets rigorous inspection protocols. You've seen railroad tracks resting on a bed of crushed stone, but have you ever considered its purpose? This unassuming layer is a hidden hero in the battle against thermal expansion. The ballast absorbs forces, drains water, and holds the track firmly in place. Without it, rails would shift and buckle under thermal stress. Its role is so critical that engineers meticulously select and maintain this material to ensure long-term stability. How does something as simple as crushed rock contribute to such a sophisticated system? The answer lies in physics, geometry, and a deep understanding of material behavior. From the clanging iron rails of the past to today's seamless steel tracks, railroads have come a long way. Behind their apparent simplicity lies a world of innovation, from continuous welded rail to the strategic use of ballast and anchors. These elements work in harmony to manage thermal expansion, ensuring safety and efficiency. The next time you see a train gliding effortlessly down the track, take a moment to appreciate the brilliance of the engineering beneath it. Railroads don't just defy thermal expansion, they harness it. turning a natural challenge into a testament to human ingenuity. This journey through railroad engineering showcases not just the science, but the stories and struggles that shaped it. Whether you're a history buff, a science enthusiast, or someone who simply loves trains, there's something magical about uncovering the secrets of the steel veins that connect our world.